Hello and welcome to this video lesson on Bond enthalpies, and the content in this video lesson appears in two parts of the specification, those with reference 3.1.4.1 and also 3.1.4.4. So our learning objectives for this video lesson are: firstly, we want to define, understand and use the terms bond enthalpy and mean bond enthalpy. Then we want to be able to calculate enthalpy changes, whereas before in the previous video lesson we just dealt with enthalpy changes qualitatively. Now we're going to actually calculate in kilojoules per mole what the enthalpy changes actually are, and we're going to use mean bond enthalpies in that process. After that, we will explain why values from mean bond enthalpy calculations differ from those using Hess's law. So obviously we'll have to understand Hess's law first, and then we will compare the mean bond enthalpies calculated with Hess's law compared to those published. And then lastly, we will want to recall the definition, because you can be asked in the exam just to define standard enthalpies of combustion and formation. So those are our lesson objectives. Let's start with an explanation as to what are bond enthalpies. And let's do that by looking at a couple of examples. Let's draw a water molecule. We've got oxygen and hydrogen in a water molecule, and let's compare that to let's say a methane molecule with carbon, and in carbon's case we've got, in methane's case we've got hydrogen atoms there. So what we have here is in the water molecule we have two covalent bonds between the oxygen and a hydrogen. And in the methane molecule we have four covalent bonds, each are carbon-hydrogen covalent bonds. Okay, so they're all covalent bonds, but they're of different strengths. Some are stronger than the others. And what a bond enthalpy is the bond enthalpy is the energy required to break a bond. Energy required to break a bond. Okay, so if the bond is strong, it's going to require more energy to break it, and so the bond enthalpy is going to be higher. Whereas if it is weak, so not all covalent bonds are the same strength, if it is a weak covalent bond, it will require less energy to break it, and therefore the bond enthalpy for that bond will be lower. Okay, so that's that, and that defines what bond enthalpies are. But one last point before we move on, and that is about breaking bonds and making bonds. So obviously it takes energy to break a bond, so you have to put energy in, and so that's an endothermic process. And bond making, so when you've got the individual atoms and they combine to make a product, so you've made new bonds, usually covalent bonds, then that is bond making, and that gives out energy, and so that's an exothermic process. So let's just write that down. As we've got bond breaking, and we're saying that bond breaking requires energy, so that's putting energy into the system, so that's endothermic. And bond making, so in the process of making bonds, energy is released, and so that's coming from the system to the surroundings, so that is exothermic. And what we can also say is that if bond making energy required. Let's switch that around. Let's say bond breaking. If the energy required to break those bonds is greater than the energy released when bonds are made, then clearly delta H is going to be positive, and so that's endothermic. Whereas if the energy that you need to break the bonds is less than that which is released when you make the product bonds, then clearly delta H is going to be negative, and that is an exothermic reaction. There. So let's have a look at a little example, a real example. Let's consider the reaction between nitrogen gas and hydrogen gas. So we have nitrogen gas, and we react that with some hydrogen, and we're going to make ammonia. Okay, and to balance this we need 2 moles of that and 3 moles of this. And we can write the displayed formula here. A nitrogen molecule looks like this with a triple bond, and you've got a single bond between each of the hydrogens, but you've got 3 of them. And here in the ammonia molecules you've got nitrogen and 3 hydrogens, but you've got 2 of those molecules. Like that. So let's have a look at these bonds. So on the reactant side we've got this triple bond between the 2 nitrogen atoms in the nitrogen, and we've also got a covalent bond between each hydrogen molecule, but we've got 3 of them. So let's try and do a little bracket like that. So the energy required to break all those bonds in both the nitrogen molecule and the 3 hydrogen molecules is 2,253 kilojoules per mole, like that. And the energy required, the energy released when these 6 bonds, these 6 nitrogen-hydrogen bonds are formed is 2,346 kilojoules per mole, like that. So what you can see is that the amount of energy released, 2346, is bigger than the amount needed to break, 2253. Alright, so that means that the reaction is going to be exothermic because delta AH is negative. The amount of the difference between the 2346 and the 2253 is released to the atmosphere. So it's an exothermic reaction. So now you know what bond enthalpy is. It's just the energy required to break a bond. But what about mean bond enthalpies? Well, that is just the average of all the different types of a particular bond. So take the carbon-carbon bond, for example. You've got a carbon-carbon bond in methane, you've got a carbon-carbon bond in all the alkanes. So you can see that you get lots of carbon-carbon bonds in different molecules. All right? Each of them are going to be slightly different strength depending on the electronegativities of the other parties that surround your carbon-carbon bond. And so what we do is we calculate a mean of all of the different carbon-carbon bonds to give you a mean bond enthalpy for carbon-carbon that you can then use in various calculations. And that applies to all the different types of covalent bonds, even within a molecule. So let's have a look at an example of a water molecule. So let's draw our water molecule first. Let's have our oxygen and our 2 hydrogens and our 2 bonds. Okay, so there's our water molecule. Now, what we have in this water molecule is 2 covalent bonds. They're both oxygen-hydrogen covalent bonds. And let's say we break the first one. How much energy is that going to take? So let's use a blue color. So we're going to break that bond, and that's going to cost us 492 kilojoules per mole to break the first oxygen-hydrogen bond in a water molecule. But then what we have is we don't just have a water molecule left. Right, so let's just draw what we have as a remainder. You've still got the oxygen there, you've got a hydrogen, and you've got a covalent bond. So it sort of looks the same, doesn't it? Except what you also have is you have a negative charge there, because the hydrogen has left just as a proton, and oxygen has kept the 2 electrons in that covalent bond, such that the hydroxide ion that we have left has a negative charge. Which means that if we wanted to break this oxygen-hydrogen bond, I've drawn it in a slightly different blue because it's still an oxygen-hydrogen bond, but it's in a different molecule. It's now in a hydroxide ion instead of a water molecule. Okay, so if we wanted to break that, it would take us a different amount of energy to break. So that would take us 428, slightly less energy to break that bond. And the reason why it's different is because of this negative charge here. The oxygen has some negative charge associated with that extra electron, the electron that is pinched off the original hydrogen, and that weakens the bond between the oxygen and the remaining hydrogen. And if that weakens that bond, it's going to take less energy to break it, hence 428 kilojoules to break a mole of those bonds, compared to 492 kilojoules to break an oxygen-hydrogen bond in an unbroken water molecule. So if we wanted to calculate the mean of these 2 bond enthalpies, it's a simple calculation. We take our 492 to break the first oxygen-hydrogen bond, and we take our 428 from our second oxygen-hydrogen bond. We've got 2 of them, and we want to calculate a mean, so we divide it by 2, and that gives us an average or a mean of 460 kilojoules per mole. And that is our mean bond enthalpy for the oxygen-hydrogen bond when we consider these 2 molecules, the molecular ion of hydroxide and the water molecule. However, if you were able to look up into a data book the bond enthalpy for the oxygen-hydrogen covalent bond, you will notice a figure of actually 464 as it happens, kilojoules per mole. Right, and that's even different to the mean that we calculated of 460. And that's different because where the data book will calculate the mean of lots of different oxygen-hydrogen bonds. We'll also look at some alcohols and some carboxylic acids as well as just these 2 examples. So when you consider lots of different bonds, then calculate the mean, you're going to get 464. So that's the value you would see in your data book. Okay, so what we're going to do now is we're going to have a look at example of calculating enthalpy changes. And in order to do so, let's have a look at an example. Okay, here what we're going to do is calculate the overall enthalpy change for the reaction we considered earlier with nitrogen reacting with hydrogen gas to make ammonia, according to that balanced equation. Okay, but before we get into the detailed calculation, let's write down a generic rule that we can follow. So the enthalpy change of the reaction, as we saw earlier, is equal to the total energy absorbed, minus the total energy released. So that's our generic equation that we're going to use in these types of calculations. And while we're at it, why don't we just use some notation? So that's our enthalpy change of reaction. We can even call that delta HR. Is going to be total energy absorbed. So that is going to be the energy that's required to break all the bonds. So energy for bonds to break the bonds minus the energy required to make the bonds. Okay, so delta H of the reaction is going to be energy to break the bonds minus energies released that's given out when the bonds are made. There we are. So let's have a look at this reaction in detail, the reaction between nitrogen and hydrogen. And what it's often a good idea to do is to actually draw the molecules. So we sort of did this before, but let's do it again. We've got nitrogen, and that's got a triple bond between the two nitrogen molecules. And then we've got 3 hydrogen atoms. So the hydrogen atoms have a single covalent bond, but there's 3 of them, and they go to make ammonia, which looks like this, but there's 2 of them, so I can draw them like this. And instead, in fact, instead of writing 3 times that, why don't I just make it even simpler and draw 3 of them. Okay, so we can see all the bonds we've got to break and all the bonds that are being made. Okay, so next step, really what we need is we need to know the bond enthalpies, mean bond enthalpies for each of these bonds. So we need the triple bond between the 2 nitrogens, we need the hydrogen-hydrogen covalent bond, and we need the nitrogen-hydrogen covalent bonds. And so we look up in a table, and in an exam you would be given the mean bond enthalpies in a table such as this. So you can see we've got we've got 5 different bonds, including all the ones we need, and their mean bond enthalpies. So let's go ahead and make the calculation. What we can do is we can look at the table, and we can look at the nitrogen triple bond, and that's 945. Yeah, and then that's what it's going to take us to break that nitrogen triple bond. And then we can look at the hydrogen-hydrogen covalent bond as 436. So this one's going to be 436, this one's going to be 436, and this one's going to be 436. So 3 times 436 to break all those bonds. And then we can look at the nitrogen-hydrogen bonds. So that's given underlined in red there. That's the nitrogen-hydrogen bonds. Each one of those is 391. So this one's 391, this one's 391. Excuse me for taking time to do this, but I just want it to be clear. So each of those nitrogen-hydrogen bonds are 391, and we are making 6 of them. So you're going to get 6 times 391 kilojoules released. So let's just write that maths down. switch back to, I'm going to switch to purple instead. So all of the bonds broken. So let's say delta H equals bonds broken take bonds made let's call it bonds formed because you might come across that word instead. It means the same thing. All right, so the bonds broken is going to be 1 times 945 plus 3 times 436. So that all comes to 2253. If you put that in your calculator, 2253 kilojoules per mole. And then our bonds formed is going to be 6 times 391, which is 2346. And when you do that little bit of subtraction, you're going to get minus 96. But let's remember our units, kilojoules per mole. And so that's our answer. That is the overall enthalpy change for that reaction, minus 96 kilojoules per mole. Okay, just to make this clear, what we'll do is we'll look at another example. So let's have a look at a different example. This time we're going to calculate the overall enthalpy change for hydrogen reacting with oxygen to make water. And just notice the half in front of the oxygen molecule. That is there because it's O2. So you can have half O2, but if it was O on its own, you couldn't have half because we can't split an atom. So that's our reaction. What we'll do first, before we do our calculation, is just draw the displayed formula of each of the components of our reaction. So we've got a hydrogen molecule, so 1 covalent bond between 2 hydrogen atoms, and we've got half of an oxygen molecule, and the 2 oxygen atoms have a double bond between them. You'll remember that oxygen is in group 6, so it wants 2 electrons to fill its outer shell, so it's going to form a double bond between the 2 atoms, and that's going to give you a water molecule like that. Okay, so now next we can write our formula. So our enthalpy change is going to be bonds broken take bonds formed, like that. And so our bonds broken, so we're breaking the reactant bonds, so we've got one of the hydrogen bonds, and we've got half of the oxygens, and the bonds formed are our 2 oxygen hydrogen bonds. So let's look at our data table for those main bond enthalpies. So our hydrogen is this one here. So we're going to have 1 times 436 plus half of our double bond oxygen. So that's half times 498. And we don't really need to put it in brackets, but let's just make it double clear. And we're going to subtract from that 2 times our oxygen hydrogen bond, so 2 times 464. Okay, and so when we multiply those out, we're going to get minus 243 kilojoules per mole. An exothermic reaction to the tune of 243 kilojoules per mole, which is our answer. Okay, let's move on. To our learning objectives, just to check that we have done it all. So our first lesson objective was to define, understand and use the terms bond enthalpy and mean bond enthalpy. So bond enthalpy, the energy to break a bond, and the mean bond enthalpy is just the average for that bond in lots of different molecules. So we did that, and then we calculated enthalpy changes using mean bond enthalpies. We did 2 examples of that. But in the third one, I don't think we explained why values from mean bond enthalpy calculations differ from those determined using Hess's law. We didn't do that. Okay, so Hess's law you've not come across yet, and that comes up in a couple of lessons' time. But it's an alternative way of working out enthalpy changes, but it uses the bond enthalpies for specific reactions. Okay, so the answer to this learning objective, i.e. why calculations using mean bond enthalpies differ from those determined using Hess's law, is that with Hess's law we don't use mean bond enthalpies, we use specific bond enthalpies. Okay, so that is going to cover that off as much as we need to at this stage, and we'll come back to Hess's law in a couple of lessons' time. And what we still need to do is we need to recall the definition of standard enthalpies of reaction, combustion and formation. So 3 definitions we need to learn, so why don't we try that now. So the different types of, let's write in delta H, the different types of enthalpy change are formation, combustion and reaction. So first of all, let's do formation. So we're going to write out the notation first. So it's formation, so we're going to have a little delta F there. It's an enthalpy change, so we're changing enthalpy. We've got standard conditions. Okay, so the definition of enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its elements. So it's formed, the clue's in the word formed from its elements in their standard states under standard conditions. Right, so let's just illustrate that with an example. So if we've got 2 moles of carbon, so at 298 carbon is going to be solid. Right, it's going to be graphite, and then we've got 3 moles of hydrogen gas, and at standard state at 298 it's going to be gas. Alright, and then we've got half a mole of oxygen, and again oxygen is going to be a gas at 298 Kelvin, and so they are all the elemental reactants, and so when they react they're going to form, so it's a delta H of formation, they're going to form the compound C2H5OH. Okay, and as you know, we don't need to write the 1 in there, but the reason why I illustrate that is because definition is for 1 mole of a compound. So 1 mole of ethanol in this case is formed from its elements in their standard states under standard conditions, right? So 298 Kelvin and 100 kilopascals pressure. And that's the enthalpy change required to make 1 mole, to form 1 mole of ethanol. Okay, and for combustion, so yes, combustion is going to be the enthalpy change of combustion, also under standard conditions, but this time it's not a mole of product as it was in formation, it's a mole of substance being completely burned in oxygen. Substance being burned in oxygen, and it's 1 mole. So for combustion, we're talking about 1 mole of this substance being burned, whereas if you remember in formation, we're talking about 1 mole of product being formed. So that's combustion, and lastly let's do reaction. So we've got delta H, so we've got the enthalpy change under standard conditions, but this time it's a reaction. So the standard enthalpy change of reaction is the enthalpy change when a reaction occurs in the molar quantities shown in the chemical equation. So let's write that down, molar quantities. In the balanced chemical equation. Okay, so I'm going to tell you how to remember this. So if in an exam you're asked to write down the definition of one of these enthalpy changes, then it can be a 3-mark question, and the first mark, right, is going to be for saying something about how much you're making or using. Right, so if you're being asked for the definition of the enthalpy change of formation, you're going to have to say that it's 1 mole of product formed, whereas if the first mark is for 1 in combustion, for the enthalpy change of combustion, the first mark is for stating that it's 1 mole of the substance being burned, and the same first mark if you're being asked for the enthalpy change of reaction is to mention that it's a reaction involving the molar quantities in the balanced chemical equation. So that's the first mark that you have to get. A second mark is easier. So the second mark is for the standard conditions. I'll put that in green. So that's the same for each. So you have to mention the reaction, the formation, the combustion, or the reaction is happening under standard conditions. That's your second mark. Same for each of the 3 definitions. And the third mark is for stating standard conditions. Okay, so and that is the same for each of the 3, formation, combustion, and reaction. So you mentioned the 3 things for the 3 marks: 1 mole. And that changes depending on whether you're defining formation, combustion, or reaction. But the second mark is for saying under standard conditions, and the third mark is for saying standard states. So there's your 3 marks for your 3 definitions. So very quickly, let's just check off our last learning objective as well. So before we had checked that we'd done the first 3, and now hopefully you will be able to recall the definitions of standard enthalpies of combustion and formation and reaction. So I don't know why we've missed that out there. So I'll write it in there. You need to be able to define the standard enthalpy change of reaction as well. And we've gone through those 3, and I've told you how to remember how to get all 3 marks for each of the 3 definitions. So there we are. Thank you for listening to this video lesson, and I'll see you in the next one.